Hello and welcome to the part 2 of module 5. And in module 5, we are discussing the web ontology language. And in part 1 of this module, we have discussed the different constructs that are available in the OWL language in the first place. And we have seen that there are different families of OWL, namely the OWL Lite, OWL DL, and OWL Full. And we have given plenty of examples where we can see that different class expressions can be formulated using this OWL language, right? And also, while we were working on this class expressions or the expressions in OWL, we also tried to mention the corresponding description logic form of those constructs, right? Though we have not defined the description logic form formally in those examples, but somehow we got to understand what are the kind of constructs that are there in description logic, right? And they are having one-to-one correspondence with the OWL construct, right? And then we kind of demonstrated how we can create ontology using these OWL constructs based on a tool called Protege, right? Now the next question comes, well, we have a language. From this language or using this language, we can develop an ontology. Then what? So then the next thing that we got to do is to perform reasoning over this knowledge base, either uh, to get answer to a particular query that we'll be putting to the system or this knowledge base, or maybe coming up with new piece of information or new piece of knowledge out of existing ontology that we have defined with out, right? So the reasoning will be having the center stage going forward. So this is the kind of thing that we are up to, right? Now, in order to perform reasoning over one knowledge base, the first thing that we need to do is to translate the constructs that we have defined using this OWL language into a formal setting or a mathematical framework. Otherwise, we cannot write an algorithm to perform this, that we have seen earlier, right? So the first thing that we have with us, so we have uh, an OWL database, OWL knowledge base, I will say knowledge base. And this OWL knowledge base is uh, has been created out of the OWL language, right? Now, in order to perform reasoning, then we have to map this a mathematical setting or formal setting, and then we can apply or we can devise some reasoning algorithm to work on this formal setting and come up with new inferences, and as well as to answer uh, a query, right? So the particular focus of this particular part of this module would be to talk about the formal setting that we will require to represent the OWL ontology or OWL knowledge base mathematically or formally, right? And that particular setting is what we call as description logic. So description logic is the logic or formal or mathematical framework to describe OWL ontologies in a formal notion. So in this particular module, we will be discussing on how to capture the semantics of OWL using description logic, right? So as we have mentioned earlier that mm, we had talked about different examples and we have tried to make the examples represented in both owl as well as description logic, also in first order logic, right? We have tried to represent the same thing in different ways, right? So in a sense, we have got some knowledge or notion of what description logic looks like, right? Now, to start with, let us try to summarize what are the kind of constructs that we have discussed as far as the description logic is concerned, right? So, we will be reviewing the description logic constructs that we have encountered. So, the first thing that comes into mind is something called existential restriction. This is what we have discussed, right? Existential restriction. And how does it look like? So, to provide an example, a very quick example, so maybe we can define a class like eligible for masters. Eligible for master. So, this is the class that we are trying to define, master's program. I know that if someone has got at least one UG degree, can be made eligible for masters. So, the class expression that will be that we'll have in the right hand side of this class inclusion axiom is has degree UG, right? So any UG degree you have, you are eligible for masters, right? Or maybe you can define something called KGPN. KGPN to be the subclass of someone who has got at least one degree, and that degree is a degree that is offered by KTP. So this is a bit of more complex example than the first one, offered by KGP or ITKGP. You can write ITKGP, right? So I'll discuss this kind of thing later, but let us focus on this existential quantifier at this point in time. So we can make use of existential quantifier to satisfy the thing that the kind of items or kind of entities that will belong to this class. So this is a class expression, right? And the elements or the entities that will belong to this class has degree UG. When this entity has got at least one property which has got labeled to be has degree, and the value is something that belongs to UG. And we know how to draw this out, right? So we are trying to say E1 is the entity and it has got at least one degree which is say D1, right? And D1 should be of type UG, right? Then we say that this kind of restriction is called existential restriction, right? So this is one very important construct in description logic, right? So like we have this existential restriction, we have got the other restriction like say universal restriction. And also we had several examples of universal restriction. For example, if I want to define say father of girls, right? How do we define that? Father of girls, maybe it would be a subclass of something who has got child, all the child to be say female. That's how we can define universal restriction, right? You want all the properties the entity has, and the properties has child, and the value for all these properties should belong to the female category, right? So this is so let me draw it one. I have drawn it many a times, but let us draw it one. So F1 so has child, say C1, and F1 has got child, say C2, and both of them are of type to be female. In that case, this F1 would belong to the class for all has child female, right? Now, as we have got this universal and existential restriction, there are other concepts like negation. So you can negate a class expression. Now, this scope of this negation, it can be over an atomic concept. So, for example, I want to find out something that is a complement of, say, academic class, right? So, this is we refer to this as complement of the academic class. Now, if we try to make it more generalized, so we can negate a concept expression. Now, this concept in one sense can be one atomic concept, or in other scenario it can be a complex class expression, as we had seen earlier, right? So now what will happen, it will just try to find out the set or the class that is a complement of this academic, right? So for example, let us try to represent something called a degree-less person, right? So we are trying to define something called degree-less person, right? So we can make it to be a subclass of. Now first of all, I need to represent something like a person who has got at least one degree, right? How do we represent that? We can make use of this existential quantifier and then say has degree something. And if we say something like this, we are saying that it has got at least one degree, and degree might be anything, right? It can be anything. It can be a master's, it can be a UG, it can be anything you want, right? Now you are defining this degree-less person. You say that a person or one entity. So this means an entity who is a member of this degree-less person, also it will imply that E is a member of something that does not have any degree, right? So this is how we interpret this statement, right? Now, as we can take complement over one existentially quantified expression, we can also take complement over universally quantified class expression. So let us try to define something. Let us try to write the formula first, then try to see what would be the natural language representation of this formula. So we are trying to interpret this formula as one, say, AI coding challenge. Now, how should we interpret this? Uh, so one interpretation of this would be uh, say the individuals, they will be belonging to this class, and those individuals, they will have certain property. What is this property? This individual for whom this particular thing will not hold. And what is the thing? That all the things, they have one is AI coding challenge. This should not hold. This should not hold. Right? So the other way of saying is this, of the same thing, is that the individuals who have won other challenges also. The individuals who have won other challenges also. Right? Now you can try to uh, make this equivalent to something. So if we just move this negation inward, what will happen? This universal restriction will flip into existential restriction, then has one would remain the same, and we just say not of AI coding challenge. So that means the individuals who have own one challenge or one thing that is not AI coding challenge. So that we are, with this we are following this kind of interpretation, and with this we are following this kind of interpretation. Right? Both the things are equivalent. Right? Now we have observed that we can use intersection and union of classes. So this is the other item that we have in the description logic family. So intersection and union, right? So you can define, say, person class to be equivalent to, say, male and union female, right? You can define something called, say, athlete student to be equivalent to a class that is the intersection of the student class and the athlete class. So you can take intersection and union of two class expressions, and needless to say, so what you can say that C is equivalent to C1 intersection C2 or equivalent to C1 union C2. So this C1 and C2, they can be atomic concept, they can be a complex class expression also, right? Now, as we have mentioned earlier, that this OWL ontologies, they have got some special concepts and special properties. So the special concepts are bottom and top properties, bottom and top concepts, right? And we have already made use of some of these classes or the concepts which are called top or bottom concept. Bottom concept we know it is represented. So bottom concept is represented as this with this symbol, which means owl nothing, and the top concept is represented via this T symbol, and it is equivalent to owl thing, which is basically the superclass of all the classes, and this bottom class is a subclass of all the classes, right? So one example of using this top class would be, let us try to define, say, father, right? So you are defining the class father. So father is equivalent to person and male, and if someone is a father, he has got at least one child, right? So has child thing. So it can be anything. We really are not bothered about what it be. It can be a female, it can be a male, it can be anything. But we are just happy to see or satisfied to see that this person has got or entity has got at least one child, right? Then we define that to be a father. Now let us try to revisit the definition of degreeless person, right? So degreeless person, right? So we can make it to be the subclass of someone who does not have any degree. So there are two ways to write this: someone or something that does not have any degree, right? So the first way to write this is for all has degree is nothing, right? So this is equivalent to say that uh, all all the degree is are nothing. And this is basically representing the fact that the entity does not have any degree, right? And the other equivalent way to say this, the same thing, is negation of there exists has degree t, right? So we are saying that uh, the fact that the entity has got at least one degree is false. So we are saying that the fact or the entity, so these are the individuals, individual uh, for whom has at least one degree does not hold, right? So there is something else to talk about this expression, this particular expression. Let me take this out here. So let us try to represent a person with degree, right? So the person with degree, if we try to represent it, person with degree. So it will be, we can define to be the subclass of there exists has degree T, top, right? Now these kind of using this top concept or bottom concept, what we call as limited existential form. So uh, so this is a very special case of using this existential form. So this is what we call as limited existential form, right? So you see that here we could have used something like UG, PG, PhD, something like that, right? But instead of using them, we are just saying anything, right? So this is a kind of loosening the kind of values it can take, right? So it can take either one PG or UG or PhD degree, right? It doesn't really matter. So this kind of existential form, which is not restricting you too much, uh, that kind of form is pretty easier to process than the form which has got very specific class as the restriction class or restricted class, right? So that's why this is called limited existential form. And we will see later that this limited existential form is included in simpler language families. So as we go forward, we'll see that this description logic has got different families, as OWL has got different families, right? And for the simpler families, this limited existential form is included, but the most restricted form of this existential usage is not present, right? So we'll see that later. Now the next concept expression that will be we can express in description logic is concept inclusion axiom. Concept inclusion axiom. So this is basically used to either actually define different concepts. So this is used to define concept, right? Now when we try to define a concept, in the earlier examples we have seen that there are two ways. We can make the concept that we are defining, say C, to be equivalent to some expression. This is one form. The other form is we are making this C to be subclass of, say, another class expression, say C1. So let me put C1 here. So we know the form C1 already, and we are making this C, which is the new concept. So this C is the new concept, and you're trying to make this to be equivalent to C1. And in the other case, C1 is made the subclass of C is made the subclass of C1, right? So this case is the case of defined case, so defined concept, and this is the primitive concept case. Now you can see that for the defined concept case, we are providing much more information about C than the same with this primitive concept, right? So let us take two examples of two of these things and try to see what whether the kind of meaning that we are ascribing to this particular forms is true or not, right? So let us try to define, say, grandfather. Now you make this grandfather concept to be equivalent. So this is our C, right? Equivalent to person, right? And then intersection has child T, right? So how do we really take this? So this is one entity who has got child. I'm writing HC, say C, uh, small c1, right? And this small c1 has got at least one child, which is C2. Then we say that E is a member of the grandfather, right? So this class expression is conforming to this part of the graph, right? And the intergraph is uh, representing this particular inter expression, right? And the other concept that we are trying to define is a IIT KGP robotics group name, right? So let me say KGP robotics group member. So you know that a student or an entity we is a member of this IIT KGP robotics group is also a KGPN, right? So it is saying something about the entity who is a member of KGP robotics group member, but it is not saying everything. So for example, if we say that the student has to have some excellent coding capability, so that is not mentioned here. We are just mentioning that IIT KGP robotics group member is also a KGP, right? So it provides less information as we have mentioned earlier. But this definition of grandfather is somehow in its sense a complete one, right? So it is providing much more information. So for example, if we had something like say grandfather, father is a subclass of person. So you see we are providing much less information here than this, right? So whenever we see that we have provided all the information that we want to provide for a particular class, then we use this equivalence class expression. Otherwise, we use this subclass classes, right? Now, all this kind of expression like say C is a subclass of D or C is equivalent to D, these are called class inclusion axiom. Now, these class inclusion axioms, they can be defined over atomic concepts. These are very simple class inclusion axioms, but also they can be applied in a generic sense. For example, here, this particular statement is not involving any complex expression. So these are all atomic classes. So that's why this kind of class inclusion axiom belong to simple class inclusion axiom class, right? But take this example. So this is a kind of a very complex expression. Here we are having complex combination of different things, right? So this, when again combined with negation and other things, so this is a more generic form of this class inclusion axiom. So if we allow this kind of complex class expressions to be appearing in this class inclusion axioms, those are called general class inclusion axiom, GCI, or general class inclusion axiom, right? So why these are axioms? These are, we are asserting to the knowledge base to be true. So that's why these are called axioms, right? And this is independent of any individual that we are defining later, right? So this definition of grandfather is always true as far as our knowledge base is concerned, right? So that's why these are called axioms. Now, as we can have the inclusion axioms for the concept, we can also have inclusion axioms for the roles, and that brings us to the role inclusion axiom. And as I mentioned earlier, we can use this term role to represent properties, right? So these properties and roles, they are called the same thing. They are the same thing, right? So this property and role, they are kind of having the same meaning, right? Now, so this kind of inclusion is also called a subsumption, right? And this subsumption, this, as we have this subsumption in the between the classes, We can also have subsumption between the roles and the properties, right? So let us try to see what kind of subsumption we can think of. So for example, if we take, say, has one, right? Now we can make it to be a sub-property of has participated, right? So that means whenever we have two entities, so for example A and B are two individuals, those are related via this has one, right? So A has one B, so that will imply that A has participated in B, right? So we will come to the mathematical definition of all these things that will make the things more concrete and formalized. Now, as we can have this sub-property relationship between two roles or two properties, we can have also equivalence of two properties, right? So, for example, we can say that teaches is equivalent to, say, lectures in, and also we can make this lectures in to be equivalent to, say, is taught by inverse. So this particular thing you can see whenever we have got a role name R and we put a minus sign as superscript of R, that means the inverse of R, right? So we can make two properties to be equivalent. Now this, whenever we have got this roles and their inverses, we, when we describe the formal semantics of all these things, we'll be using two terms. One is atomic roles or role names. So example of this atomic role and role names is, say, teaches. So teaches is one atomic role or also a role name, right? We want to make it distinct with role inverses. Role inverses. So role inverses is basically this R inverse or is taught by inverse. So these are role inverses, right? Now, as we have seen that we can combine different classes to come up with another class expression, we can also combine different roles to come up with new roles, right? So, these kind of combining different roles with each other and to come up with another role is called role constructor. We do that with the help of role constructor. Right? So one example that we can have for this, so for example, let us represent something called has spouse, right? Now we can define this has spouse to be equivalent to has husband and union has wife. So if X has got wife, then X has spouse, X has got wife to be Y, then X has got spouse to be Y. If X has got husband to be Y, then X has got spouse to be Y. Right. So that's why we just take the union of these two properties to come up with this new property or new role has spouse. Right. Also, we can use property chain axiom to come up with new properties. So, for example, if we try to define has father-in-law, father-in-law. How do we define that? We try to make that to be equivalent to, say, has spouse and then compose that with has father. So it is basically spouse's father is the father-in-law, right? Now you can have different other combinations. I'm not going to those. So one point that we need to consider while we are constructing roles out of multiple roles, we have the concern of decidability. So in the unrestricted form of this role constructor, will make the language undecidable, right? So that's why when we talk about these role constructors in different DL families or description logic families, we will restrict the usage of this constructor so that our language family becomes decidable, right? Now with all this, I guess that we have got all the necessary foundation to describe the uh, different families of description logic, right? So we'll be talking about the families of description logic. Now this, as we are trying to put forward from the very beginning, that there are different functionalities or different constructs that are allowed in description logic as a whole. But depending on how you are approaching your application. So if your application does not require much complex database or knowledge base, then you make use of very simple constructs from description logic. So what is the advantage of using this simple construct? There are several advantages. The first advantage is that your uh, expressivity or the language of expression would be much more simpler, right? The second thing is that you can find a very efficient support for reasoning if you have a simple language, right? But again, if your language is simple, then it might not be expressive to the extent uh, of the requirement of your application, right? So if your application requires complex way to represent or complex constructs to represent your knowledge of the application domain, then perhaps you should go for a complex version or complex family of description logic. So that's why in the community, in the semantic web community or the OWL community, there are some designated families of this description logic which have got uh, mm, use in different practical applications. So now we'll be talking about those families, right? And again, as I'm saying that we can choose and pick our constructs from the description logic. So let us see what is the simplest bouquet of these constructs that we can think of. And the simplest form of this bouquet will give us a language which we call as the attributive language. So that is the most basic DL family, and that is called the attributive language, and we represent that with a L. So I'll be using this calligraphic A and L or alphabets to represent the families because that is the convention that is used in this description logic or OWL community, right? And this AL stands for attributive language. And what are the things that are allowed here? So a class expression C, it can be one atomic concept. So this A stands for atomic concept. You can include this top concept. As a concept expression, you can have this bottom concept. Negation of a concept is allowed, but it is allowed only for atomic concept. So negation is allowed only for atomic concept, not general class expression, right? The intersection of two classes is allowed, C2 is allowed, and the universal restriction is allowed here for all R, C is allowed here, and the existential restriction is allowed but in a limited sense. So we have already discussed this. So this is the limited existential restriction. So in this sense, this if we have something like this, RC, this is not allowed in AL. Right. So let us have an example of this particular a concept expression that belongs to this particular language family. Right. So let us define, say, AI student researcher. So let us make this to be equivalent to, so AI student researcher is a student in the first place, and it is not a faculty, and uh, for all the things they have published, so for all the things they have published belongs to the domain, say AI, right? And that make sure that the individual has published at least one paper. Otherwise, we should not take that entity to be a research, right? So not of published. So let me put, say, AI paper. So at published, all the things they have published is AI paper and has published at least one thing, right? So you see that we are using this to be one atomic concept, and this uh, faculty, not faculty is an atomic concept, and we have taken negation of faculty, so this is allowed. And this here we are using for all RC, so C being this thing, this is your C and this is your R, and you are using the restricted version or the limited version of existential restriction, which is R top, right? So that's why we can say that this belong to this particular concept definition belongs to AL family, right? Now, as you have been promised earlier that we'll be coming up with a formal definition of everything that we talk about. Otherwise, we cannot do reasoning, right? So that brings us to the uh, semantics of the description logic language. So the semantics of DL, right? And if we have the semantics of DL, we can get to the point of semantics of OWL, because these OWL languages, they have one-to-one correspondence with the description logic language, right? Now, whenever we talk about semantics, We can represent semantics in many ways, but in formal uh, systems, the semantics is represented in two ways. So, semantics in formal systems, so these are the two popular ways. There might be other ways. So, one is model theoretic semantics. Semantics. And the second one being the first order logic based semantics, or FOL based semantics. So when we talk about these different families, we'll try to represent them in both this model theoretic semantics and first order logic based semantics. Right. Now, what do we do in model theoretic semantics? We try to represent everything as different sets, and we try to establish the definition of different concepts and other things using this set theoretic notation. So, in a sense, this model theoretic semantics, they are represented using the set theory, right? So, whatever we describe, so for example, the individual, the classes, the relations, they all are represented using sets, and uh, the interpretation of a particular concept expression will boil down to uh, um, operations over a complex set of operations over the different sets representing different parts of this concept expression, right? So that is what we do using this model theory, right? Now, what we will be doing using this first order logic based semantics, there we'll try to directly translate the concept expressions into their corresponding first order logic based form. And as we know that these first order logic based form, they are very formal in nature, and there are reasoners and algorithms that can infer knowledge out of this first order logic based systems. So it will be very good if you can translate this description logic or OWL syntax or OWL constructs into their corresponding first order logic form, right? Now let us first focus on this model theoretic semantics part, right? So the thing that I'm going to talk about here is generic in the sense this is applicable to any description logic family. So we have started with the semantics of this attributive language, but whatever I am going to talk about, the model that I am going to talk about is applicable to any description logic family, right? And then we try to come back to this attributive language, the semantics of attributive language, right? Now, if you consider the case of description logic or OWL, so these are kind of two things that are pretty much equivalent to each other, right? So there are mainly three entities. One is the set of individuals, the set of class names, and the set of role names. So those are the kind of things that you can find in an OWL ontology, right? So let us try to represent them, right? So what we have got individual names, right? Let us represent this with a I. So I'm representing this I with a different style. So we should follow the style that we are representing, the style of the font. This is our I, the set of individual names, right? We have got set of individual set of class names. So we have got class names, and let us represent that with C, but our C is a kind of C like this, right? And finally, we have got the role names. And these role names will be representing as this art, right? Now, in this set of individual names, you can have one symbol to be A. So this is a symbol that represents, out of many others, represents one individual, right? Let us consider a class which is the symbol C, and this symbol C is representing a class, like say class of students. So student is a class, faculty is a class, and in the set of role names, let us consider this R. This R is different than this double R, right? So this R is a symbol that represents a role name. For example, say has parent or has child. So that is a role name, and that is symbolized by R, right? So all the names that you can see in the ontology, like has child, has name, has base, has spiciness. So all these are symbols of different role names, and these symbols, they are used while you represent something in your ontology, but you need to put them into concrete terms. You need to assign with them some concrete terms so that they can be used while computation. And that is what we are really going to talk about here, right? So these are the things that we have in our ontology. So these are the kind of elements we have in our ontology. Right. Now, as I have told you earlier that so this basically is the vocabulary of your ontology. Right. Now, as I have mentioned earlier that everything, when we try to put these symbols into their grounded term, we want to ground these symbols or concretize this symbol. We make use of the set theory, right? Now, how do we interpret this symbol R? So, whenever you are saying we are trying to ground these symbols, we are trying to interpret this symbol. Interpret the symbol. So, these are all the same thing, right? So, what would be the possible interpretation of A? So, this is what you need to answer. So, what is the possible interpretation of A? So, this is one question that we need to answer. Now, what would be the possible interpretation of C? That is the second thing that we need to answer, right? The third thing that we need to answer is what is the interpretation of R, right? Now, what do we mean by individual? So, individuals, they are uh, simply different entities, right? So, they are referring to different entities. So, for example, if I say Virat Kohli, so we write say EXS, say Virat Kohli. So, this is the symbol that we are representing. We are representing the entity Virat Kohli, right? So, there is a one-to-one mapping between this symbol with the person Virat Kohli, right? And let us assume that this A, after transforming this symbol into its proper concrete term. So, let us assume that hypothetically there is a function that will map this symbol to the real Virat Kohli, right? So, that let us represent that function to be say big gamma, right? So, what does it do? It transforms, or it uh, when it takes us what it takes us input, it takes us input 1, symbol, like say EXS Virat Kohli, and map that to one hypothetical person Virat Kohli. So here we are having the person Virat Kohli, right? And the result of applying this function, this transformation function over A is say A to the power gamma. So we are just symbolizing this. So this is the result of applying this transformation function over this symbol A. And this gamma, what does it help? It help us with, or how does it help? It helps us with to find out the interpretation of A, right? Symbol, I should write symbol A. And that's why this is called the interpretation. Right. Now, if we apply the interpretation function over A, it will be transformed to A gamma, and that will be one single member in the set. So this set, we consider a set which is basically the set of all the individuals. So this set is the set of all the individuals, and we represent that with say delta, right? And this dot, as you can see here, so this dot A gamma, this belongs to the delta, right? Now how do we interpret this symbol for class name C? So what is a class? A class is basically again another set, right? And inside this set we have got different members, different individuals as members. So we can represent this C, we concretize this C, or we ground this C, or we interpret this C as a set which we call as C superscript gamma, which is basically the result of applying this interpretation function over this C, right? And finally we have R, right? So R is the set of role name. So what would be the interpretation of R? So again it will be a set. The interpretation of R would also be a set. Now here we have got this individual instances as members, right? But here the member of this R to the power gamma set, so this is the R to the power gamma set, it will be containing different pairs of entities that are related via this R relationship. So basically we will be having a set of such pairs. So for example, if we have say captain of relationship, so this R is equivalent to say captain of, right? Now what it will contain? It will contain something like say Virat Kohli, captain of India. Ian Morgan is captain of UK, so on and so forth, right? So all these would be the member of this, right? So you can see that we have one function which is basically the function gamma, which is the interpretation function that maps different entities or different elements in the ontology to their corresponding grounded form. And this in the ontology, what we have got only symbols, right? either an individual or a class or a role name. Now, by using a set, what we are doing, we are trying to make these symbols grounded or make these symbols concrete. So, how do we make one individual to be concrete? To find out the proper referent for that, and that will be a single entity, right? How do we find the concrete or grounded form of a class? The grounded form of a class would be a set containing different individuals as members. What would be the grounded form of R, a relation? It will be a set of pairs of entities that are related via this particular relationship R, or symbolized by this relationship name R, right? So with this, let us try to look at what is the kind of form of this interpretation function, right? So as you have seen earlier, so this uh, stylized I is basically the set of symbols for individuals and the C, stylized C, is the set of symbols for the class names. I'll say individual names. I should not say individual. Individual names. Okay, you are using symbols, right? So that will be classes. And finally, we have got stylized R, which is basically the set of symbols for roles, right? Now, how do you define this interpretation function? We are defining interpretation function gamma, right? So for that, we need to have a domain of interpretation. And this domain of interpretation is basically we represent that with delta, and this is the set of all the individuals, right? So again, let me tell you that this individual is this set is different from this set of individual symbols. So these are the set of symbols, but this delta is the set of real things, right? You can think this set delta to be the set of real things, right? Now to have a mapping, we have to have a mapping from the individual symbols to the domain elements, right? So let us represent that part of this mapping function, which is your big gamma I, right? So this gamma I, what does it do? It basically takes us input one individual symbol and map it to delta, one element in delta. So what you have? You have this set and this set. This is the set of I and this set of delta, and you have a mapping from this I to a delta, right? So the mapping can be one to one or one to many, right? So that doesn't really matter, right? The second thing that we need to have is to map. We have to have a mapping from the class names or class symbols to so it will be a set, right? It will be a mapping from the name to a set, and that set should be a subset of the domain, right? Subset of the domain. So that's what we have seen earlier. Let us go back to the earlier slide. So here you can see that this particular set C gamma is basically a subset of delta. So this is your delta. So C gamma is a subset of delta, right? So, and what kind of subset it can be? This C gamma can be one empty set. C gamma can be having a singleton set including one member. So it can be any possible subset of this set, right? So this this particular subset is basically any possible subset of delta. And how do we represent that kind of thing? We can represent that kind of thing as a power set, which is represented as 2 to the power delta, right? So gamma C is basically a mapping from the set of class symbols to 2 to the power delta, right? So a class symbol is being mapped. So a class symbol C is being mapped. So this is the set of all the class symbols, and this is C, and this is being mapped, and this is your 2 to the power delta, which is basically containing different sets, different subsets of delta. And this C is being mapped to one such subset, right? So finally, you got to have something which is a mapping from the role names to, so what will it be mapped to? Basically, it will be mapped to the set of pairs of binary relations involving the domain element, right? Now let us consider that you have the domain of elements to be delta, right? Which is basically the set of all the individuals, right? Now let us consider that, well, you have relations between every pair of individuals in this particular domain. So if we have got that, so the set that will be representing all possible pairs would be the Cartesian product of these two. So this will represent all pairs of individuals, right? Now, given one relation R, a subset of these pairs, would be participating in R, right? So let us consider this set to be say S, right? Now what is R then? So R is basically should be mapped. So again, you have a set of role names. So there is a set. So this is the set of role names, and out of this set you have one element which is R, right? Now what R will be mapped to? So R will be mapped to a subset of this, will map to a subset of S, because R will not hold for every pairs of the domain element. So for example, if you take all the persons in the universe, right? Now if I say has father, right? So there will be a subset of all the pairs you can think of in this universe of these persons. A subset of them will be participating in this has father relationship, right? So basically this R will be, so this is your S, right? And which is basically delta cross delta, and R will be a subset here, and you can think of many other subsets which are uh, inside this set S, right? So how do we represent all possible subsets of this set? We can represent that with 2 to the power S, which is basically equal to 2 to the power delta cross delta. And what will be R? R will be mapped to a subset of this, right? So 1 out of this 2 to the power delta cross delta. So our delta R would be, so it is a mapping function which maps this R to 2 to the power delta cross delta, right? So here we have all the possible subsets here. So this set, I should not say S, this will be 2 to the power S, right? Or 2 to the power delta cross delta. So this is the set of all the subsets of delta cross delta, right? So the interpretation function of I would be mapped to delta. Interpretation function of C would be, C will be mapped to 2 to the power delta, and R, the interpretation function of R would be, you are mapping R to 2 to the power delta cross delta, right? So with this, let me stop here, and in the next lecture we will try to connect this to an example, and we'll try to see what we really mean by an interpretation for a given knowledge.